Great, so let's practice finding some antiderivatives. Okay, so the idea here is that we know, given a function, how to take its derivative, right? We have a bunch of rules about how to take a function and find its derivative. What we want to do now is actually reverse the process, right? So what if we are given a derivative? How do we find a function that goes along with it, right? So a function whose derivative will be what we were given. Okay, so given these functions, right, we're going to use these as the derivative, and we're going to find another function whose derivative is equal to each one of these. Okay, so we're reversing this process. That's why it's called antiderivative. Okay, so let's start with the first one here, x to the fourth. So we want to find a function whose derivative is going to give us x to the fourth, right? So we want a function where if I take its derivative, it's going to give me x to the fourth. So if you think about it for a little bit here, you might think, what about x to the fifth? Because if we take its derivative, right, so d dx, it's going to give us 5x to the fourth. So that's not exactly right, because we have this 5 out here and we just want x to the fourth. So then you think you have to scale this a little bit, right? So what if we took the original function, multiplied it by 1/5, okay? And then in that case, I would have had a 1/5 hanging out there, and then I would have taken the derivative, which would have given me this 5x to the fourth part. And then look, you would have this 5 and this 5 cancel, so you're left with just x to the fourth, right? So if we think about this then we can take this 1/5 x to the fifth, right, put it up here, and then let's think about its derivative, right, just to check. So the derivative of 1/5 x to the fifth, so the 1/5 is just hanging out there. Differentiate x to the fifth, that's going to be 5x to the fourth. The 5's are going to cancel, and then you're definitely left with just x to the fourth, right? So this 1/5 x to the fifth is exactly what we're looking for, right? So the way we write that down is the antiderivative, so this little s-looking symbol is antiderivative of x to the fourth, is 1/5 x to the fifth. And because this notation, this fancy s with the dx, means the general antiderivative, right? When it doesn't have numbers down here, it means the general antiderivative. Then we have to put in a little plus c at the end here, right? Because really, if I stuck in an extra constant at the end there, it doesn't change the fact that the derivative of 1/5 x to the fifth plus some constant is going to be x to the fourth, right? If I did a plus 1 out here, its derivative, the derivative of the plus 1 would be 0, so I would still get this, right, x to the fourth. Okay, so this is the general antiderivative of x to the fourth. Okay? And actually, I'll mention here that there's a more general rule. So when you're finding the antiderivative of x to some power n, okay, if you're finding the derivative of x to the n, what you do is you add 1 to the power, so we'll have n plus 1, and you divide by the new power, right? So then you're going to have times 1 over n plus 1. And then, of course, you have that plus c. Okay? So if you look here and here, right, the 1/5 x to the fifth, that's exactly this part, right? 1 over n plus 1, x to the n plus 1. Okay, so if you're integrating or finding the antiderivative of x to the n, you just add 1 to the power and divide by the new power. Okay? So now let's think about the next one, right? So number 2 is e to the x. So if we want to find the antiderivative of e to the x, we're thinking about what function has a derivative equal to e to the x. And if you think about it for a little while, e to the x is special in that it is its own derivative. Right? So actually the antiderivative of e to the x is also just e to the x. Right? So if I take e to the x, find its derivative, it will just be e to the x. Right? And because this is supposed to be general, I'm going to stick a plus c on here. Right? So if this was e to the x plus 2, its derivative would still be e to the x. Okay? Let's think about the next one. So 1 over x. So 1 over x, right? We're trying to find the antiderivative of 1 over x. This means we're thinking to ourselves, what function can we find can we take its derivative and get 1 over x, right? So what function has derivative equal to 1 over x? So if you think about it for a little bit, you will probably come up with the function ln of x, right? Ln of x, its derivative, we saw in a previous week's notes, its derivative is 1 over x. So there's only one subtle thing here going on, in that because we were given this at the start, the only number that this can't be on the denominator here is 0, right? The denominator can't be 0. But notice there's no problem with letting x be negative down here, right? It's perfectly fine to take x and have it be negative in the function 1 over x. But we can't have x being negative over here in the ln. Okay? So actually the antiderivative has to take that into account, and we actually need absolute value bars in here. Okay? So this antiderivative isn't exactly right. What you need truly is ln of the absolute value of x, okay? Because you need to make sure that you're not doing anything silly and you're not plugging in negative numbers into this ln. Okay? So we're using this as the antiderivative. So this should be ln absolute value of x plus c. Okay? And then the very last one here, so the antiderivative of minus sine of x dx. So you're thinking to yourself, what function has a derivative that's equal to minus sine of x? And I bet you can pretty quickly get to the function cosine of x, right? So if you think about what's the derivative of cosine, its derivative is exactly minus sine. Okay, so the antiderivative of minus sine should be cosine. And then we stick this plus c on there, right? Because this is supposed to be general, right? General antiderivative.